Professor Power.
Yes, what can I help you with?
This is Levant. This is
Yeah.
Levant Tillery. Just confirming, this is still counted as participation and whatnot, right?
Yeah, as I'm asking questions and you're typing your answers into the chat, that still counts as participation, so don't worry.
All right, sweet. Thank you.
My pleasure.
And just to confirm, sorry about this, but Friday we are coming in class to do the exam.
Yeah, the exam's going to be in person. It's going to be written.
Yep. All right, sweet. Thank you.
Thank you. All right, well, let's get started. Just a couple of quick things. Just a reminder, the exam is this Friday. It's going to be written. It'll be in person. You'll fill out a Scantron sheet. Just makes the grading a lot easier. It's 50 multiple choice questions. Pretty straightforward. Covers everything from earth materials, geologic time, plate tectonics, and earthquakes. We're going over tsunamis today. That's not going to be on this first exam. That'll be on the next exam. Since it's a Scantron, be sure to bring in a pencil, number 2 pencil, or else there might be some discrepancies in the grading process, and that'll make it harder for me to figure out which questions you got right or wrong. So keep that in mind. Make sure to bring some pencils. We can use that full block of time that we allocated for this class, 1 hour and 45 minutes. Plus we can go probably till 2 o'clock. I can stretch that a little bit. If you still need more time, let me know. We'll just move it to my office, which is a bit of a hike, but I'd rather you guys take the time that you need to get the exam done and get it done well, rather than rush you through it. That's how we'll approach that if we need more time on the exam. Does that sound good to everybody? All righty. What else? If you haven't gotten your relative dating exercise graded, it's because I don't have it. I don't have the submission, but I extended the deadline. So if you haven't submitted it, please do so I can grade it. Everyone did pretty well on it. Well done. Keep up the good work, and that'll be good to study for the exam as well. Tsunamis is going to take all of today and some of tomorrow, so I figured I might put together a quick little exam review, just ask some questions that'll test your knowledge, that'll help you for the exam on Friday. So make sure you're present for that. Otherwise, let's get started. So we do tsunamis after we talk about earthquakes because the two are often tied together, and one often follows the other one. This glorious image is from that cinematic masterpiece 2012. You guys remember that movie? Back when we thought the Mayans had predicted the end of the world and everyone was going nuts. What a terrible movie, and John Cusack is a terrible actor. That's all I can say about it. But luckily, tsunamis don't look like this, but they are still pretty devastating. So what is a tsunami? It can be a series of massive waves, but it is not a tidal wave. Tidal waves are what we experience on a normal daily basis. Tides occur because we have the moon orbiting the Earth, as well as the Earth is orbiting the sun. Those forces of gravity are pulling on each other, and that pulls water in these different directions. So whenever the sun and the moon are in line, we have a much larger tidal cycle because they're pulling in the same direction. Whenever they're perpendicular to each other compared to the Earth, you get a much smaller tidal cycle. So it's not tidal, it's a completely random event, and it's not part of that tidal system. So it's caused by a sudden violent vertical displacement of matter on the seafloor. So if we take a bunch of rock and when we throw it into a river, that water gets displaced. If you continue to fill up that body of water, the water will continue to rise. So if you have a sudden violent displacement of water, that water is going to go up and then it's going to spread out in all directions, which is what we see whenever we look at tsunamis. So far, only geologic hazards can cause tsunamis. There's not been an instance of human-induced tsunami that we know of. So luckily, sadly, we can't prevent them, but we can learn a lot about them and learn how to prevent them from being so damaging. So we have a couple of possible causes for creating a tsunami. So volcanic eruptions is one. This is less than 5% of tsunamis. We've seen the mid-Atlantic ridge, we've seen mid-ocean ridges, those divergent boundaries where we have that volcanism coming up. Sometimes those eruptions, usually they're very gentle, but sometimes they can be pretty violent and build up a lot of igneous material rapidly. That rapid displacement may cause enough displacement to cause a tsunami. So if you imagine just having your hand at the bottom of a pool and pushing up, you're pushing that water up and it's going to create a wave on the surface. Sometimes if it happens on land, like in Kilauea, if we have a large enough displacement and a fast and rapid enough displacement from those lava flows, we can get a tsunami sourced from terrestrial volcanic eruptions like the Hawaiian Islands, the Aleutian Islands, where there's a lot more explosivity. But if we do have a violent enough eruption, what will most likely happen is we'll have a collapse of that volcano. As we're erupting, we're destabilizing the rock itself. Part of it can collapse and fall into the water. That's what happened in Russia along the Kamchatka Peninsula. If anyone's familiar with that region, it's the one right across from Alaska, the one where you could take a look from your house and see Russia. It's still part of the Pacific Plate, so it's volcanic island arc or a peninsula arc. So it has a lot of explosive volcanoes there. So one good example is Krakatoa, which is erupted in 1883. This was an incredibly violent eruption. This was felt all over the world. There was some guy in London that said he felt it, which it's not very scientific. He probably didn't, but it was still pretty widespread in its effects, mainly because the ash columns and the gases that erupted from it caused a global cooling event. It was only like 0.1 degrees, but it was still pretty significant to have that from one violent eruption. And there was also a darkening of the sky from this. Lots of ash, lots of debris. So this sent, if you look at that image to the left, part of that volcano is collapsing. That dashed line is the original shape of the volcano. And all of that matter is just being sliding and slumping right into the ocean. So that's your source for your tsunami wave. You're getting this massive body of rock falling into the water. It's displacing all of that water. It's going to send it out in all directions. So just from that source in Indonesia, if you can see on that map to the right, it's reaching all over the world. It's traveling into the Atlantic. It's traveling all over the Pacific. Luckily, a lot of the island nations behind Indonesia were kind of shielded by Indonesia. So plus the main directional force of it was westward. So that definitely helped them as well. So the Atlantic got a bit of a brunt of it. It took a long time to get there, but they still felt the effects of it. So another possible cause is a landslide under or into the water. There have been some landslides. If you imagine the continental shelf, where it's all underwater, but there's this big drop off where we reach the ocean basin. If any of those start to destabilize, they can slump. That still causes a displacement of water, except it's in the opposite direction. The water rushes to fill that void space, and then there's a sloshing effect, and then it spreads out on the surface. But this is an example of a landslide on land that goes into the water. So this is Lituya Bay. That's in Alaska. This happened in 1958. So not a lot of people living in this area. This caused about 3 deaths, if I remember correctly. Most of them were fishermen that were just right off the coast here. So if you look at the shape of the bay, specifically with that map there, it's very narrow. And it has some pretty steep sides from the mountains. It's almost a fjord like you see in Norway. So the combination of this earthquake, which caused this rock slide, dumped 90 megatons of rock into this water. It ends up creating a gigantic splash wave, 530 meters in height. And the main reason for that height is just because of it's so narrow. If you imagine having a large bowl and dropping things into it, it's not going to rise so high. If you have a much smaller bowl or even a glass of water, it'll rise a lot higher. So if you narrow down that surface area, you're going to increase the height that the wave can get. So that's why Lituya Bay was such a huge wave, just because it was stuck in this narrow channel. It didn't stay that high for long though, just because the moment it got out into the ocean, it's kind of spread out and dispersed. It still reached Hawaii, but it was only 10 centimeters tall. So if you can imagine 10 centimeters as probably about that, that's not something to worry about really. But yeah, biggest one recorded in history. So the most common cause of tsunamis, though, is earthquakes, specifically earthquakes that happen at subduction zones. So we've talked about plate tectonics. We've talked about how earthquakes happen, and the most damaging earthquakes, the most strongest earthquakes happen at subduction zones. This is an example of how and why that happens. So we have our subducting plate. In this case, we have our oceanic plate subducting because it's a lot denser, it's heavier. The overriding plate looks like it's continental because it has some dry land there, so it's much lighter in density. So it's going to be the overriding plate, whereas the denser stuff is going to subduct into the mantle. As that subducting plate is passing beneath it, we're going to get friction. These plates aren't perfectly smooth, as we see in this model. They're rocky bodies. They've got all these jagged edges that are going to catch and get stuck on each other. So along this little portion here, we're going to get stuck on that overriding plate. So that's at that zone of friction that we get. So as we move, that locked plate is going to bend. And this is still an elastic material. The plate as a whole is pretty elastic. It's pretty rigid. It wants to come back to its original position. So as you get this deformation from the original shape, you're going to get a deeper trench right at the base of it. And you get this bulging effect along the back where that mass has to go somewhere. So it's going to bulge up in the back end of it. It's going to decrease in the front with the compression. So this locked fault zone is really dangerous because we're incorporating a lot of stresses into it, and it's building up strain. It's continuing to build up strain. Because it's a large plate, it can handle a lot of strain. So we're going to keep raising up that pressure, raising up that force until that energy gets released and it snaps. Because it's an elastic, because of the elastic rebound, it snaps back into its original position. And as you can imagine, all that water has just, that originally settled into that trough has now been pushed up, right up to the surface. And that just spreads out in all directions. So you end up getting a localized tsunami and a distant tsunami. So as that wall of water is pushed up from the seafloor, gravity takes care of it and it goes in all directions. So it falls back down, but it moves as a whole wave. So you have your local effects landward, your distant effects out to sea. If you're out at sea at the center of a tsunami, you probably actually won't really feel this. The sea in the center of the ocean is swelling normally, and if you're out there on a boat, you're not going to notice it at all. It's not until you get closer to the land that you really notice these violent effects. So where are all the global subduction zones? The well-known ones are here in yellow. Man, whoever made this map was a goddamn moron. Look at how terrible that looks. Oh my goodness, that's awful. Okay, well, I digress. But as we can see, all these subduction zones are surrounding the Pacific plate. In the Pacific Ocean, we know we get a lot of tsunamis in the Pacific Ocean, more so than the Atlantic. But we do have some subduction zones in the Atlantic. If we look at the Caribbean, right off of Cuba and Haiti, we have the Caribbean plate subducting underneath part of the North American plate. And we also have some subduction zones on the other side of Central America, which if the earthquake force is strong enough, it can spread over to the other side of the isthmus. We also have a lot of subduction zones on the western side of the Pacific. This is where we get all of our trenches, the Marianas Trench, the Tonga Trench, the Soda Trench. These are really, really deep portions of the earth. So they can hold a lot of water, and if all that water is displaced there, that's where we get our most destructive tsunamis.
Excuse me, Professor?
Yeah, what's up?
Oh, we can't see the slides.
You can't see the slides.
It's seem to be frozen on the first page.
All right, let me try stopping the share again and starting it. How's that? Can you see it now?
Yes, it works.
Okay, if I change, does it work still?
It doesn't seem like it. Oh, yeah, it did.
Okay, perfect. Okay. So in order to understand tsunami waves, let's talk a little more about wind-driven waves, the normal waves that we experience. So we have all of these air currents all over the earth, and they're moving in pretty standard directions. in a pretty stable flow. So the entire ocean as a body of water is experiencing these oscillations. So if you look at the bottom of this image, you have these slight oscillations in the water particles. They have this circular motion, and it's a small motion, and that as soon as you get deeper and deeper, it becomes negligible. But as you get closer and closer to the surface, those oscillations become greater and greater, and that's where you get those sinusoidal waves. That water is traveling up over the top of that cycle, down back into the trough, and that's why you have those crests and troughs in oceanic waves. So we have just like we did with our seismic waves, we have a wavelength in between the crests, measured from crest to crest. We have the wave height measured from the trough to the top of the crest. And we have a typical direction of that wave motion. So it's really similar to seismic waves. All waves really behave in the same way. So with wind-generated waves, they're shallow and they have a very short period, 5 to 20 seconds. So very, very small in their size. So tsunami waves, though, have a lot larger wavelength, longer, 100 to 300 kilometers. The reason that you can't tell it's a tsunami in the deeper ocean is because you can't even tell what's going to happen in 100 to 300 kilometers. Like you're out in the middle of this vast space and you can't tell anything. So they can travel over the entire ocean. They don't lose energy readily. They're not like seismic waves where the energy dissipates as they travel through material. Since the ocean is pretty much more of a homogeneous fluid, it transmits that energy pretty readily. So it doesn't lose that energy until it hits land. That's where we're going to lose our energy. So they can travel a very, very long period of time for a very long distance. And as you can see, there's just that one crest. The next crest is kilometers away, hundreds of kilometers away. So there's no way you would even tell. These also have very long periods. Instead of 5 to 20 seconds, we're getting minutes to hours. So very long periods of time in between each of the crests. So you can't really detect it if you're in a boat at all. So being in a boat is not the best way to, if we wanted to have a warning system, just having a navy of boats and people on those boats, they wouldn't be able to perceive it. So it wouldn't be very effective. So all of that energy gets transmitted all the way to the shoreline. So as we're getting closer to the shoreline, we're going to decrease our depth. If our tsunami started at the middle of the ocean, we have a very, very large depth all the way to the bottom of the ocean. As we're approaching the shoreline, that depth decreases. We're coming up to the shore, going from 4,000 meters at some points to 50 to 10 meters. So that wavelength is going to shorten drastically. So that's where we get these larger, taller waves that we see at the shoreline during a tsunami. So that's going to continue up until it reaches the land, and then it's going to crest over and eventually hit the shoreline. So you guys have probably seen shoaling. If any of you have been to the seashore and been to the beach, the moment where the wave breaks, this buildup of all of these waves that get closer together. You can see these in real time at a smaller scale with normal tidal waves and wind-driven waves. As they get closer and closer to the shore, if you look out further, they just look like a wall of water. And then eventually they're going to get taller and taller until it reaches the point that it crests over and it breaks. So we see the same thing in tsunamis on a much larger scale. So how big are tsunami waves? Most of them are not very large. Honestly, they're 0.5 to 1 meter. But that's relative to sea level. So if you have your coastal infrastructure built around normal sea level, 1 meter is up to my waist. And that's of that's full water everywhere, all over the place. So if you're at, let's say, 0.5 meters above sea level, most of your infrastructure is 0.5 meters above sea level. Your sewage, your electric, your pipelines is all buried underneath that. Just 1 meter is going to be really devastating. But they can get to up to 10 meters in height. So Japan, just in case you didn't know, tsunami is not an English word. The Japanese have been studying and dealing with tsunamis since the beginning of civilization there. Tsunami is derived from Japanese, and they know the most about them. So they've been dealing with them for a long time. A lot of their villages and infrastructure during their earlier periods were built higher up on the land to avoid these. So the biggest one that happened in Japan in recent history was in 2011. This caused the Fukushima Daiichi disaster. This was from the Tohoku earthquake that we talked about the last 2 days, that magnitude 9, that huge one that happened at a subduction zone. Remember, we have the strongest earthquakes at subduction zones. And we have a max wave height of 10 meters here. You can see that it's spilling over something. That's actually their seawall. So their seawall, they've had these before. So they built a seawall in this harbor to prevent anything from pouring over. The seawall was not high enough in this case. Or actually, it was high enough, but there were some other things that happened that we'll get into that caused it to spill over. And then another tsunami that we've had recently in 2004 was over 30 meters high. And this one was the most devastating, probably, I think, 300,000 deaths from this one particular event. So let's do a little quiz. Which represents the amplitude of tsunami wave the best? Wavelength, wave height, water particle motion, water movement, or ocean depth? So how many people think it's A? How many people think it's B? C? D? How about E? All right, very good. You all did really well. It's wave height. Remember, amplitude, whenever we were talking about seismic waves, was the measurement from the trough to the top of the crest. That's our amplitude. Wave height is pretty much the same exact thing. What's the most common cause of a tsunami? Landslides into water, landslides under the water, earthquakes at subduction zones, or underwater volcanic eruptions? Who thinks it's A? Who thinks it's B? How about C? Or D? All right, very good, guys. Earthquakes at subduction zones. These are our most powerful earthquakes on Earth. It makes sense that they're going to be the most common cause of tsunamis because it takes really big events, really big displacements to create tsunamis. So let's take a look at 2 different tsunamis, 2004 in Indonesia and 2011 in Japan. Both of these were really high magnitude events from the earthquakes that produced them. Both of these happened at subduction zones, and there's a lot that we can learn from both of these. So let's start with Indonesia, 2004. So we have the India-Australian plate subducting underneath the Sunda plate, which is a microplate. Don't worry about looking into microplates. All the large plates on Earth are broken down into these smaller structures that helps us understand movements a little more. You guys don't have to worry about that. All you have to know is that the Burma microplate is a lot lighter and less dense than the India-Australian plate, which is why the India-Australian plate is subducting underneath it. Same thing that we had in that model before, where that overriding plate gets locked and then it starts to get pulled downward and downward until eventually we're going to build up that strain until we get our breaking point, and then it snaps back into its original position. So at subduction zones, remember, we have these deep oceanic trenches. And this is a very long trench. The Sun Trench is 3,200 kilometers long. and over 7,000 meters deep at its deepest point. So that's, let's see, we're 7,000 meters. What is that? 3 Freedom Towers deep, I think. Freedom Tower is how? No. Yeah, Freedom Tower is 1,776 feet high, I think, if I remember correctly. So yeah, little over 3 Freedom Towers deep. So that's pretty deep, and that's not even the deepest point on Earth. The Marianas Trench is over 10,000 meters deep. So as we get that displacement, we're going to get this huge megathrust fault where it's coming back up to the top. So if you look at this model, all this is going to start building up. And this is what these kind of earthquakes look like when they're mapped out along this trench. We have so many of these in this area. As you can imagine, this is pulled from the USGS site. They maintain a pretty well-kept earthquake activity database. This is updated every 5 minutes with every earthquake that happens around the world greater than 3.0. So the larger the circle, the larger the magnitude of the earthquake. On the map on the left, I'm not exactly sure what the color denotation is, but yeah, it's typically the larger the circle, the larger the earthquake. So in the image to the right, we have our large magnitude 9.1 in 2004. We had another larger one in 2005, some in 2012. So we have a lot of different large-scale earthquakes happening at this subduction zone. And then we have all of these little earthquakes that precede and occur after those larger earthquakes. These little 3.0, 4.0, the aftershocks, the foreshocks, those are happening at the same time. So the epicenter of this was at Sumatra. Sumatra is one of the islands of Indonesia. It was obviously a magnitude 9.1. On the modified Mercalli scale, we're looking at an 11, so super, super violent. The earthquake alone was super violent, and the tsunami was even worse. So this was felt in Banda Aceh, which is the capital of the Aceh province, and it's the 3rd largest earthquake ever recorded. What is the second? I think the second was in Alaska, and the first but most violent earthquake ever recorded was in 1960, Valdivia, off the coast of Chile. So this is what that town looked like right before the tsunami. A lot of coastal infrastructure, a lot of people living on the coastline, big fishing population there too. It's the largest city in this province, and it's the entire maximum elevation is 35 meters. So the highest you can get is a little over 100 feet above sea level. So this is some footage of that tsunami coming in. So you'll see the wave breaking in the back. I'm sorry for the grainy footage. This is from 2004. They didn't have smartphones back then. This guy had to grab a camcorder, which most of you probably haven't seen for quite some time. So as it gets closer, those waves start to break and break over, and now it starts to spill over into the land. And whereas other waves that you see at the beach, they recede after they break, the tsunami just keeps coming, and it just keeps going, because remember, we're dealing with this huge mass of water. It has to go somewhere, and it wants to go somewhere. And it's going to keep going up and up. As you can see, if you have bad building practices, it's going to sweep up underneath anything that doesn't have a proper foundation, and it's going to pull it out. So a lot of the problems that come from tsunamis, it's the initial shock of it. The water keeps coming. It breaks away anything that was anchoring a building or structures down. And then as that recedes, it's going to pull everything with it. So some people are able to survive the initial impact, but they don't survive being swept out, because some people end up getting caught in it, they're swept out far into the sea, kilometers out into the middle of the sea, and then they end up drowning. So this is what that city looks like immediately after the tsunami. As you can see, it swept over the entirety of the island. Remember, this tsunami was 30 meters high. The entire island is only 35 meters high. So if you were lucky enough to get to the hilltops, you might have survived. But if you were anywhere below that, you were probably done so. So this ended up killing around 300,000 people total. Just in this area in Indonesia, it killed 167,000 out of a population of 200,000. So that is an overwhelming population loss in that area. So remember, we're going to have two different tsunamis occurring. This is occurring off the coast of Indonesia. So that was all from the local tsunami. This is what immediately went towards Indonesia. We have a distant tsunami that's going to go outwards into the Indian Ocean, as well as travel into the Pacific and even reach as far as the Atlantic. So let's try to figure out how fast do tsunamis move. Most of this is dependent on water depth. This is the equation that we're going to be dealing with for tsunami velocity. V stands for velocity, D is water depth, G is the acceleration of gravity, which is 9.8 meters per second squared, and that's raised to the half power. So let's do an example of this. So let's say the tsunami occurs at 4,000 meters in depth. We want to calculate its velocity. So how would we go about this? Remember, V equals dg raised to the 1/2. So go ahead and grab your calculator and let me know what you get. Let's actually figure that out too. Whoop. All right. What do you guys think? Who has an answer for me? What do you got? 200 meters per second, 2,000 meters per second. That could go to space. But yeah, it's 200 meters per second. So did everyone else get a similar answer? Probably got 197 point something. Yeah, so that's what we're working with. 200 meters per second. So how far is 200 meters? That's 100 meters is about 1 football field. That's going the length of 2 football fields in a single second. So imagine you're in that tsunami and you're traveling that distance just in a second, just like that. That's crazy. Absolutely nuts. So we can also convert this into something else, some more familiar terms. If you're not usually used to working with meters per second, that's what we use as scientists frequently, just because the metric system is a lot more easy to convert things. But 450 miles per hour, that's what we're working with. Probably half the speed of most NASA rockets. Okay, so this graph is showing water depth versus wave velocity. So as you can see, as we increase in our depth, we're increasing also in our velocity. This is on a somewhat exponential scale. 7,000 meters, we're getting roughly a velocity of 943 kilometers per hour with a wavelength of almost 300 kilometers. If they're formed in deeper water, they usually end up traveling faster. That means they have more energy because there's more mass behind it, and they're more devastating. So if we know that the most devastating tsunamis occur from points where the water is deepest, let's take a look at some of the deepest points on Earth, which are oceanic trenches, which happen right along subduction zones. So we have the Aleutian Trench. The Aleutian Trench is right next to the Aleutian Islands in Alaska. That's over 7,000 meters deep. The Sunda Trench, which was creating that tsunami in Indonesia, roughly the same amount. The Peru-Chile Trench, right along Chile, where the Nazca Plate meets the South American Plate, around 8,000, and Marianas Trench, in the deepest trench in the world, the deepest point in the world, at almost 11,000 meters deep. Granted, we haven't even been able to hit the very bottom of the Mariana Trench yet, not even with robots. Deepest we've gone is 35,000 feet. Yeah, looking at this image to the right, Mount Everest, the entirety of Mount Everest from base to peak could fit inside the Marianas Trench. That's how deep it is. Absolutely crazy. Okay, so this is what we're looking at for same earthquake in 2004 in Indonesia. So we have that localized earthquake that went right to the immediate right, east, hit that island and devastated it. As you can imagine, even though that we're moving at incredibly quick speeds, 450 miles per hour, people on the other side of the ocean still have some time to prepare for it, some time to evacuate, to get to higher ground. So each of these lines are ISO lines. They're connecting lines of equal time. So that's each of those hours. That's how much it would take, how long it would take for the tsunami to reach that point. So Sri Lanka, one of the closest islands to the west, we're looking at about 2 hours of warning from the moment that tsunami happens. Granted, that's not enough time because in 2004, the Indian Ocean didn't really have really good tsunami warning systems. They didn't have any active buoys in the area, so they didn't have much time to prepare. So they have about 35,000 deaths occurred there. That number that you see at the bottom is the number of deaths. Obviously, Indonesia had the highest because they were right there. They had no warning whatsoever, no time to evacuate. Once we get to the north, we're getting into Myanmar, Thailand, Bangladesh. They had a little more time to prepare, so we had significantly less deaths. Thailand suffered pretty greatly. India suffered pretty greatly as well, but they had a little more time to prepare. And then you get all the way out to the other side where you have Kenya, Tanzania, Somalia, Yemen. Kenya, Yemen, they had some pretty decent tsunami preparedness. Kenya is a world leader when it comes to geology too. A lot of geologists in the entire continent of Africa end up going to Kenya just because the East African Rift is right there. So they have a lot of geologists and a lot of seismologists that work there and study there. So they had some very good warning systems. So they only had one death occur from this. But then you have a country like Somalia that didn't have as much infrastructure in place. They didn't have as many scientists in place to develop warning systems. They had 289 deaths, but they had around 7 hours of warning for that. Okay. So why do we have so few deaths in Malaysia? Of course, even though the tsunami is moving in all directions, there's still some obstacles in its way. It's going to keep going until it can't go any longer. So as it's entering the coastline, that's where it's starting to lose its energy. Remember, it doesn't lose energy as it's transmitting across the ocean. That's why I was able to reach all the way to Kenya and Somalia and Tanzania. But once it gets to the coastline, that's where we're dissipating our energy. We're losing it because it's hitting, finally, friction. That's what's going to make that tsunami die down. Malaysia didn't even experience much shaking just because it's further away from the trench. And most of Malaysia is not very coastal, surprisingly enough. Most of the coastal areas are for fishing, a little bit of trade, but Malaysia is a pretty big financial center, actually. So they have a lot more development inland. Okay, so this is the death toll and the number of damages. We have $20 billion in damages. That's in 2004 money. So that's before the 2008 recession. So we're probably looking at double that in today's money for damages. Affected 14 different countries, 233,000 people killed or missing. So this was a huge, huge and devastating event. Really took a long time for Indonesia to recover from that. So after that, they realized, most of the nations in the Indian Ocean realized they needed a warning system. So this is where we get the Tsunami Information Center, started in 2006. And they created a lot more seismic stations on dry land in the area to try and study earthquakes, to collect earthquake data. They also were able to get some seismic stations underwater, which is incredibly expensive, incredibly hard to do. So they only have a few of those underwater. One of the most effective ways are these dart buoys, which work with tidal gauges. They're basically these buoys that sit on top of the water. There's a lower portion of that that's connected to the seafloor. It senses a tsunami. It sends a signal to the buoy. That buoy sends a signal outward to all receiving stations. So they have a little bit more warning time. But from all these 22 buoys that were initially sent out by 2016, all of them have been destroyed. Every single one. A lot of the seismic stations, those are powered by electricity, but some earthquakes knocked out the electric grid, and that completely knocked out their seismic stations as well. The warning sirens are also powered by electricity, and since a lot of the nations in this area don't have secondary power sources, and they don't have backup generators, there was a lot of problems with evaluating that. But since then, they've gotten a lot better. So there's a lot more buoys in the ocean now. That's what DART stands for, Deep Ocean Assessment and Reporting of Tsunamis. Scientists do love their acronyms. There's entirely too many acronyms in the scientific community. But it's easy to remember. It's flashy, it stays in your head. So you get a 1-minute warning of strong shaking. It'll send out text messages to most people in the area. It's linked up to government systems. So people can receive tsunami warnings within 10 minutes, enabling them to get to higher ground. And that system continues to monitor the tsunami as it develops. So this is what it looks like in practice. You have that buoy at the bottom, measuring pressure. It's recording pressure. Any changes in pressure, it's going to send a signal up to the buoy at the top, which is going to communicate to everywhere in the area. And as you can see, since 2004, they've grown a lot with these buoys. It's difficult because they're incredibly expensive, and once they're out there, you can't maintain them just because they're hard to access once it's out there. As you can imagine fixing complex scientific instruments on land and how hard that is. Now add ocean water and terrible weather, and the platform you're standing on is bobbing up and down. It makes things very difficult. But we've grown a lot in this entire tsunami defense system. We have numerous tidal stations recording data, numerous deep ocean tsunameters, and so many seismograph stations all around the Pacific. just recording data and enabling us to study it. This is what that coverage looks like. As you can see, the US has a different system, mainly because we invested a lot of money in earthquakes, so we don't get a lot of tsunamis that hit the coastal United States, particularly the East Coast, but there is a risk of tsunamis on the East Coast. But we developed our own system independently from other areas. But that data is also shared with all the surrounding countries in the Pacific. Okay, so that was the 2004 Indonesia tsunami. Now we're going to look at the most recent devastating one that we had, the Tohoku earthquake that caused the Fukushima Daiichi nuclear disaster. This was a similar magnitude, 9.0, 9.1, also at a subduction zone where the Pacific plate is going underneath the Okhotsk plate. The Okhotsk plate is what's forming Kamchatka, that peninsula up to the north. That's also volcanic. So these are all volcanic arcs that we see here, and these are where we get our strongest earthquakes still. So very similarly to what happened at Indonesia, we get a locked plate. That plate continues to build up energy, build up strain until it reaches its breaking point, snaps back to its original position, displaces water again. But the rupture area of this one was huge, 400 kilometers long and 150 kilometers deep. That's enormous. That's an enormous fault system to rupture. Happened right off the northeast coast, and it moved the entire island as much as 4 meters, which is crazy. So it moved laterally in one direction. At the same time, it subsided 1/2 meters. So if you think about that image where the plate is being locked, remember we get uplift in the back end of that locked plate and subsidence here. Once we snap that back to our original position, the point that had risen before is going to sink back to its original position. So that's where we're getting the subsidence. So if you think about the island of Japan building everything based on that 1/2 meter that they had, now they don't have it anymore. Are you going to work? There you go. So this is what the earthquake looked like in Tokyo at that point. Tokyo wasn't hit by the tsunami too hard, but the earthquake was pretty devastating to it. Even though the epicenter of that earthquake was much farther to the north, because of where Tokyo's local site geology, remember those local site conditions transmit energy differently. This is what the tsunami looked like. It's moving cars, it's moving debris, buildings, everything. The people of Japan have lived with tsunamis for a long time, so they know they have a lot of safety training to get to higher ground and evacuate quickly and efficiently. Everything that water is rolling around, that's the seawall that came right over. And if you imagine the seawall, once the water is in, it has a hard time getting out. So then you're going to have the long-term effects of stagnant water, continued flooding, stuff like that. So this is what happened. This is where the plates moved. You see that rupture, that thrust fault that brings it up about 4 meters. And we can see that wave propagate throughout the entire ocean until it finds something to hit. Now, something you'll notice, I'm going to pause and go back a little bit. So look at the bottom one. So this is the sea level. Something that people notice whenever they're on the coastline of a tsunami. you'll see that the water recedes very far, almost a mile out. So if you're ever on the coastline and you see the water just recede incredibly far, imperceivably far, you should probably run, because the water's building up and building up that closer wave to come and crash up onto the land. This is what it looked like after. Trees were, everything was stripped off of the trees. Anything that wasn't tied down was swept out to sea. And that's what the wave looks like in real time. This is displacement, measuring displacement. The left is horizontal displacement, which direction the Earth is moving. Let's look at that again, because that was a pretty good figure. The right is vertical displacement. So as you can see on the left, that's permanent displacement. It's not bouncing back. Okay. So this is that time map that we saw with the Indonesia tsunami. Now we're applying it to the rest of the Pacific. Luckily, at 2011, we have a lot better of a warning system. So we see a lot of these things way ahead of time. Hawaii was the main concern here, just because this thing was moving incredibly fast. And since Hawaii is at the center of the Pacific, it's going to get a big hit from it. Luckily, they had 6 hours of warning time, so they were able to evacuate places from the coastline. There were a couple of people that died in Hawaii, maybe I think 30, but they were mainly ignoring a lot of those safety precautions. As you can see, it also hit the United States, right in Cali. That was a pretty big hit area, but same thing. Enough early warning systems, they were able to evacuate. And by the time that it reached South America, this wave wasn't really much of anything. It was very, very small at this point. All right, let's take a quick, let's do 10-minute break. Then we'll talk about seawalls and whether or not they worked or not. So go ahead, use the bathroom, grab some water. We'll meet back at 11:08.
Professor?
There it is. Okay, so we mentioned seawalls before. Usually, when it comes to planning for seawalls, most people think about the strength of the wall itself. Most people cite Hurricane Katrina in New Orleans in an example of where levees and seawalls can break and cause further damage. So most people are concerned about the actual structure of the seawall, not so much the height. Most people think 10 meters is good enough. So in this example in Miyako, this is one of the hardest hit areas. It's in an inlet. The harbor itself is in an inlet. So remember Latuya Bay, where we had that narrow, those narrow sides, which caused the water to rise. The tsunami in Miyako was also 10 meters, which sounds great because the seawall was 10 meters. So you'd think, oh, it would just lap over the sides, maybe some flooding, nothing too much to worry about, right? Well, what if the land itself sinks by a meter? So if you have the coastline drop because of the earthquake, now your seawall technically is at 9 feet. And the tsunami is still at 10 feet, or so, excuse me, meters. So all of that water is going to cascade over the side. So something that they couldn't plan for was massive rapid subsidence. Like imagine that's me going from standing on that table to the floor in no more than half a second. That's crazy. That's absolutely crazy. So there's no way to plan for that. So a seawall in this case wasn't helpful at all. And actually it was worse because once it gets in, as I said before, it has trouble getting back out. So you have persistent flooding, you have to pump that water out or redirect it somewhere. And because it's seawater, if it gets pumped out and redirected into, say, irrigation, that can be damaging to crops, that can be damaging to plant life. Also, as you can imagine, since it's flowing into the street, what runs underneath the street? Sewer lines. So that's all going to bubble up. So then not only do you have a natural catastrophe, you have a biohazard issue as well. So that's why seawalls sometimes aren't very effective. So in terms of damage, in Japan itself, we had 15,000 deaths, 2,000 people presumed missing. So most likely at this point, they're presumed dead. And as you can imagine, it's not just the immediate effects of it, it's also the after effects. So over 200,000 people became homeless. So you probably have some deaths occurring because of that you could probably contribute to the tsunami. Over 1 million buildings damaged, 4.4 million without electricity. This tsunami is hitting everything. So if you imagine how we had our earthquake example where public infrastructure is damaged, freeways, so ambulances can't get to people they need to. That's a secondary result of an earthquake. Same thing with tsunamis. If you don't have power, if you don't have water, you're going to have a lot of people die from it. So this ended up costing 235 billion, which even though we had less deaths, we had much more economic damage than the 2004 earthquake. Tsunami and earthquake. Most of this was due to the Fukushima Daiichi nuclear reactor. That was the biggest problem of it. For some reason, the Fukushima reactor was not built properly. It was built right on the coast. It had some seawall support, but not enough. So they flooded the reactor, but it caused a meltdown, which in turn polluted the water. So they had to pump everything back out. So a whole other thing adds to your costs immediately. So if we can't prevent tsunamis from happening, the least we can do is learn something about these tragic events and how we can plan for it and prepare for it and hopefully prevent more deaths from happening in the future. So we have a known and geologic history of tsunamis. Like I said before, Japan's been dealing with tsunamis since the Stone Age, and they've written about it in their recorded history since that time. So we have a long actual historical account of tsunamis and how they've been dealt with in the past. We can see where they've occurred, how they've occurred, why they've occurred. We know the geologic setting. Obviously, we know the most damaging ones happen near subduction zones. And we can also evaluate the geography, the actual land portion of it. What does the relief look like? Local relief meaning elevation changes. What is the vegetation? Can vegetation help us prevent devastating tsunamis from coming up? And then, of course, that leads to runoff, which is the water coming up through the land as far as it can go and then receding. So how do we find geologic evidence of tsunamis? You dig a hole and then you look for things that don't make sense, basically. So if we're looking at this hole here, we see a lot of these significantly delineated layers. So if we find marine sands and sediments in an environment where there wasn't an old ocean, remember these are sediments, so they should be coming from the land. But if we get, as you can imagine, a tsunami digging up sand and all those marine life forms that live in the sand, they're going to deposit those on the shoreline. Those deposits will end up getting buried by the normal typical deposits that it sees from like the uplands of the mountains. So you'll see basically an event layer that just stands out to you of sand, marine life, stuff mixed in, broken shells, maybe debris as well. Maybe there was some vegetation that got mixed in with it that should have been on the surface, but now it's just buried with all of this marine sediment. So you can see all of this from just digging a hole and looking at different layers. So we can learn a lot from it. All right, so this is a review for calculating a recurrence interval. So remember, we calculated recurrence intervals for earthquakes. So let's go ahead and do some math again. So we have this pit that's dug in India. It shows 4 large tsunami deposits, including those from the tsunami in 2004. So, and we're also going to use our radiocarbon dating, knowing what we know about half-lives of different isotopes, to find the oldest tsunami event in 800 BCE. So we have 800 BCE. Remember what BCE is and how that accounts for our normal calendar. And we have 4 large deposits. So we have 4 events. So how do we calculate our recurrence interval? So go ahead and do the math on that. Let me know what you get. So that should help you a little bit. So who has an answer? Mm-hmm. $933. That sounds right to me. That's exactly right. So does everyone still understand how recurrence intervals work? So since we're talking about the interval, you don't care about the number of events, you care about the spacing between the events. You have 4 events, you have 3 spaces in between the events. So that's what we care about. The recurrence interval. So that can help us evaluate. Whoops, is that too dark? That's better. So that can help us evaluate how often these types of events occur and when we can, it's a kind of time range that we can expect it to happen again. So well done. We can also analyze different vegetation types and what we see on the land surface. So remember, James Hutton said the present is the key to the past. Same thing is true in the reverse. The past is the key to the present. So if we understand what happened back then, we'll understand what happens today and in the future. So this is a picture from Washington State. This is called a ghost forest, where we have all of these standing trees, still standing and everything, but no vegetation whatsoever. No foliage, no leaves on these trees at all. So we've seen similar events in Canada after the Alaskan earthquake in 1964, where we had all of this flooding that occurred, spread out over all of these boreal forests. All that salt water ends up killing a lot of the vegetation. So if we can see that we have these periods of inundation that end up killing these trees, doesn't knock them over, but it just kills them from the inundation of the salt water. These aren't coastal vegetation types. They're not used to these long periods of saline inundation. They're used to fresh water. They're used to having more of a dry period, getting all of their moisture from the soil, fresh water from the soil. But something that occurs during these events, as we know, we have uplift to raise the elevation. That gives us a dry area that trees like this can plant themselves, germinate, and then grow. And then once we have that snapping motion, we have the plate goes back to its original position, and then it subsides, allowing the water to come further and further inland to just inundate this area. Eventually, it's going to kill the tree. So this terrain, if we look at the soil deposits in this, it's going to look like a tidal marsh. Tidal marshes are defined by these types of grasses that can live in saline inundation. They thrive on saline inundation. You can also see as the seawater rises, marine life will come with it. So you can see evidence of like fiddler crabs burrowing into the sediment. So you can see that in the geologic record as well. So that enables us to put the pieces together and see what actually happened. So we can also just look at the regular geologic deposits, like the rocks, the sediments, and we can see what doesn't make sense. So if we look at the deposits from all the way from Northern Cali to British Columbia, we get the same deposits. Remember, lateral continuity. These sediments deposit in long layers until there's no more sediment. So if we have the same types of deposits from California to British Columbia, there must have been a huge event of similar type that happened at the same time to bring those deposits and put them there. So if we can map that out, we can really determine that the most likely source of this was one big tsunami happening over almost 4,000 years ago along the coast. We also want to analyze the geographic risk. Geography influences the run-up, which is the height of the water onshore at its furthest point. So obviously, we know that whenever the tsunami is building up in the water, it's not losing its energy, it's not dispersing, it's moving as one big mass. And because the ocean is just one homogeneous fluid, it's not going to disperse anything. Once we're getting up closer to the shoreline, we're introducing friction to the mix. We're going to slow down that tsunami. We're going to reduce that wavelength. It's going to crash over. It's going to keep going until it loses energy and then it recedes. So that point where it loses all its energy and recedes, that's the high run-up elevation. That's the highest to the point that it went. So key difference to make here, run-up is the vertical portion of this, inundation is the horizontal portion of this. So run-up, we're looking at just the elevation, how high it got above sea level. Inundation, we're looking at how far inland that it got. So this is in the map view. The previous one is in the profile view. So in the map view, we're going as far as the edge of that blue line. That's the area of inundation. That's where we get the horizontal flooding. Remember, water takes the shape of whatever vessel that it's in, since it's a liquid. So it's going to spread out in all directions. So the inundation line is something that we can map out. It's mappable. And obviously you can imagine that the shape of the shoreline is going to influence where the run-up elevation is, where the inundation occurs. So if we look at this shoreline, we have this nice beach right along these cliff sides. So you'll imagine that everything on that flat, gentle beach is going to be devastated by the tsunami. The run-up elevation may go up to the sides of the cliff. It may channel all of that water into that flat area. Think of Latuya Bay with all that water coursing through that narrow channel. But it's not going to get very high. It's going to lose energy relatively quickly because it has to go through such a steep elevation change. So it's not going to get all the way up to the top. So if the tsunami happens there, the best thing you can do is make the climb. And obviously vegetation also helps with protection from tsunamis. Think of, well, what's a good example? If anyone is familiar with what mangrove forests are, you find them a lot in tropical areas. They're these kind of short, squat trees that have these really dense root systems. They're found on the shoreline. They really like saline inundation. That's where they really thrive. So as tsunamis get closer, they're going to take the brunt of most of that energy. If you think about, remember how we're dissipating energy as we increase friction. Those vegetation sources are going to increase the friction. And the more friction that we have, the more and the faster that we're going to dissipate the energy of that tsunami. So if you can have vegetation like certain areas and estuaries where you have that really good fertile soil that can build up different types of vegetation that can handle the brunt of this, you're going to develop a really good shield against tsunamis. One thing that we have in the state of Delaware, if we were to have a devastating tsunami, which most likely we won't, but the risk is always is never zero. Delaware has a lot of salt marshes, tidal salt marshes on the coastline. And these act like, and I want you to imagine a sponge on the coastline. There are these really thick deposits of soil with these low-lying grasses, and these grasses have huge, huge root systems. So they dampen that wave velocity and they absorb all of that energy. So that's why there's a lot of coastal salt marsh studies going on in Delaware right now, because there's such a really vital resource in a number of ways, but one of them is also coastal protection. We may not have tsunamis, but we do have hurricanes frequently on the East Coast. So if you imagine if Hurricane Sandy hit Delaware instead of New Jersey, those salt marshes would help to take the brunt of that blow. Obviously, land use. We're humans, we're developing on the land. We are a geologic force. So we're going to, everything that we do on the land surface is going to have broader implications as to what happens. So if we have vegetation areas that can absorb that energy, that's great. But if we if we cut those down for economic sources, then we're creating areas that can just be swept out to sea that aren't going to dampen that energy. Like if we build seawalls, if we build seawalls in one area, but not the other, that water is going to preferentially flow somewhere else. It could hurt somewhere downstream. It could go up the channel and go back into whatever city you're protected with the seawall. So land use is a really, really important thing to consider when it comes to protecting against tsunamis. Not to mention coastal cities, we build parking lots, we build roads. Those are impermeable layers. The water can't enter into the ground there. So you're basically creating pathways where tsunami water from wave action is going to preferentially flow. Let me understand this map. Okay, so this is the island of Oahu in Hawaii from a 1946 tsunami. And this is a run-up map. So each of those numbers along the coastline, that's the maximum elevation of the run-up. That's how high that the water got at that specific point. So if we look around, the highest example is 27 at Kahuka Point, right up there to the north. The lowest, probably Waikiki Beach, lowest elevation there. That arrow is the direction of the tsunami. So it makes sense that a lot of the higher numbers, except for this one at this point over here to the southeast at 36, but most of those higher points that took the brunt of the tsunami from the same direction, those had the highest run-up elevation. Now, once we get down to these areas to the south, we're dissipating that energy and we're decreasing the energy of that tsunami wave. And right here at Waikiki Beach, there's a lot more vegetation, there's a lot more land spread out, as well as the cliffs to the north, so that helps with keep that run-up elevation down. But we can get a lot of variation in one area. Oahu is not a super huge island, just from one event. So something that geologists do frequently is we're really good at map making, especially risk assessment maps. So this is Huntington Beach, way down in, where is Huntington Beach? Is that Cali? It has to be Cali. But these red areas on this map to the left, those are high risk for tsunami runoff. There's probably not of infrastructure built in place to prevent the tsunami runup, so that's why those areas are at high risk for tsunami runup. If you can see that red box, that's the pier, so that's an area that's a lot more built up. That's why it's in the yellow. That's why it's not at a high risk. So we have all of these risks that, all these factors that play into tsunami risk. So much stuff that we have to take into account in terms of establishing to have a proper plan of evacuation, of protection. So we have the size and depth of the fault rupture, which we can't control at all. The fault rupture is where it does because that's where the stresses are built up the most. We have the depth of the water. Deeper the water we have, the more devastating the earthquake is going to be. So if you have deeper water, you're going to have more displacement of water, which means you're going to have more energy in that tsunami. The closer you are to the epicenter, if you're a population center that's very close to the epicenter, like in the 2004 earthquake, you're going to have a very little amount of time to react, very little amount of time. You may not even know it. Obviously, population density, as we said before, more people live in more places. So the more people live in more places, the more natural disasters they're going to experience as a whole. So we have a general trend that's increasing in the experience of natural disasters. Obviously, topography takes into account with local nearshore elevation. If you have steep cliff sides, that'll help protect it against it. Gentle slopes, you might get washed away. Obviously, vegetation, education, and warning time, those are going to take into account as well. So going to be really important to think about. All right, so let's look at America as a whole. Where are we most likely to get a tsunami? I know it's hard to see, but A is basically Delaware. Nope. Man, I can't even see it on this thing. A is New York. B is going to be the Delaware area. C is southeast Missouri. D is going to be the Utah area. Nope, that's not Utah. That's Nebraska. And E is going to be the coastal California. This should be an easy one. Where's the biggest risk? A, B, C, D, or E? Everyone all together. Very good. You guys are smart. It is E. Pacific coast, obviously next to the Pacific Ring of Fire, where we have the most amount of subduction zones, the highest risk for the strongest earthquakes. Stronger earthquakes means more risk for tsunamis. Let's skip that. So if we look at the history of the specific states, we can analyze the risks of different areas. So Alaska, Hawaii, very high risk because we have high frequency of events. Hawaii, mainly because of its location. Alaska, because of the plate tectonics in the area. Alaska's at a subduction zone. Remember, the Aleutian Islands are volcanic. And they have a lot of recorded run-ups greater than 10 feet. So that's also very concerning, both of those areas. Relatively high hazard. We have Washington, Oregon, Northern California. There is a subduction zone in Washington, but it's not a very deep trench. So there's not a huge risk. They have Seattle, Washington has like a very, very high risk of a huge devastating earthquake, but it's probably not going to create a huge tsunami. There's just not enough water. But they have a lower frequency of events. The recurrence interval is 1 every 500 years. So that's very, very far apart. But the Cascadian subduction zone, you have magnitude 9 earthquakes, high potential. That's where the Juan de Fuca plate is subducting underneath North American plate. And it's continuing to stretch and stretch and stretch. And eventually, like a rubber band, it's going to snap back. So there's a very, very high potential for potentially the biggest earthquake we've ever seen in that area. If you're interested in reading about that, there's several articles that get published every year saying Seattle is going to be destroyed within the next few years. And it's, of course, a reporter making a sensational article. But just like as we talked about with earthquakes, we can't predict the future. We can only forecast. So there is, what we can say is there is a high potential for a magnitude 9 earthquake in this area during this time period. And that time period has been the last 100 years and the next 100 years. We don't know enough about the forces in play here. That being said, I wouldn't live in Seattle. And then, of course, very low hazards on the US East Coast. We've only had 6 tsunami run-ups on the East Coast in the last 200 years in our last recorded history. 2 were from the Caribbean subduction zone. Remember, the Caribbean plate is subducting underneath the North American plate, and parts it's subducting underneath the South American plate. The Caribbean is just sinking everywhere, basically. So we have this subduction zone. It's not a very deep subduction zone. As you know, the Caribbean has those crystal clear blue waters. You can see the bottom of the ocean there. So it's, even though it's oceanic crust, it's very, very shallow. So we're not going to get very deep trenches there. Not enough water can get displaced to create a tsunami. But one of the worst ones that we had was from hurricanes. Hurricane Sandy, for example, we had 10 meters entering New York Harbor. That same amount entered most of coastal New Jersey. A lot of you, some of you have mentioned that you lived in those areas and experienced that. That must have been awful, but I'm glad you got through it. But that is a very high risk that we have on the East Coast from hurricanes, because we get them every year. And they keep coming earlier and earlier each year. All right, how many more do we have? I'm going to try to rip through this in the next 8 minutes, because that means you guys have more time tomorrow for a review session. Does that sound good to everyone? All right, I figured. So this is just more of the same stuff, and that establishing an assessment for a global tsunami hazard. It makes sense for most of the islands in the Pacific, most of the Pacific coasts, very low risks in the Atlantic. There are some high risks in the Mediterranean, though. That's because there's a huge fault system there. They get a lot of earthquakes there. There used to be a subduction zone there as well. There's still some subducting plates there, so they get some pretty serious earthquakes. So coastal Italy, Sicily, parts of Greece, Cyprus, they'll get a lot of earthquake and tsunami risk. So how do we mitigate against this? So we cannot 100% predict them, and we absolutely cannot prevent them. Water is the most powerful force on this planet. You give water enough time and enough space, it will cut through anything and it will mow down anything, guaranteed. But what we can do is we can develop engineering and different structures and different engineering practices to help prevent mass death and devastation from these events. We can't stop the water, but we can stop our homes from being washed out with it. So this is an example of tsunami resistant engineering. So most people notice after the 2004 tsunami that all of the concrete houses with solid foundations, they didn't get swept away. All the shanty towns, all of that temporary housing, that got swept away, obviously because it wasn't well built, it wasn't built up to code. There was no foundation locking it into the bedrock. So if you have a 2-story house, it's able to withstand up to 2-meter waves. Also, if you have the bottom half of your house act as more of a channel, it's allowing that water to flow through rather than crash up against it and enact some forces and stresses that might knock it loose. It's going to flow right past it. And as long as you're up on the 2nd floor, you should be fine. A good rule of thumb, though, if you are ever caught in a tsunami, get up to the 3rd floor if you have one, just to be safe. Good rule of thumb is get to the 3rd floor of a concrete building. Also, as we learned from Japan, taller structures we can engineer them to reduce destruction. Just like how we reinforce things with concrete and rebar to prevent against earthquakes, we can prevent collapse from tsunamis as well. If you're out in the open, Japan has developed a lot of these. These are just evacuation towers. It's literally just a platform on stilts, and they have these at intervals along the coastline. All you have to do is run up the stairs and that's it. You're safe from the tsunami. That's solid steel in concrete. That concrete is embedded into the bedrock, so it's not going anywhere. Plus, it allows the water to flow underneath you, even if there's any debris, because tsunamis tend to carry cars with them. Anything hits that, it'll probably preferentially flow around it. So we mentioned the seawalls and how sometimes they're ineffective. There's a bit of controversy around new seawalls developing in Japan. These things are huge. If you think about that safety traffic cone is probably up to here. So that's probably maybe 20 feet tall, 25 maybe. So these are huge structures. So part of the controversy is that if the land subsides, it's still going to go over the wall. So what is the point of spending all of this money, which is around $12 billion, to build these seawalls if they're not going to work? Not to mention, obviously people live on the coastline for a lot more than just economic reasons, because they want to look out on the ocean. There's an aesthetic portion of this. So looking out and just seeing walls and walls of concrete on the coastline is probably not preferential to a lot of people. So it also lulls you into a false sense of security. Oh, the seawall is going to protect us from the tsunami. Well, it may not. It may even be more damaging. If it's not built properly, it may even collapse, causing even more devastation. So it could be a problem that people think that they're safe and they may not evacuate properly when they really should. So that's part of the controversy about building around these. Also, these are incredibly damaging to marine ecology. Coastlines develop the way they do due to natural forces. So if you're enforcing a blocking mechanism on that, you're going to drastically impact marine ecology. But the real thing that saves lives is education. Toshitaka Katada was a seismologist. He studies tsunamis, and he developed a lot of safety plans. So he developed personal tsunami evacuation maps, developed ways on different routes away from schools, from residential areas, and he did all of this training in different schools in his area. Because of this, they had 99.8% survival during this most recent tsunami in 2011. So knowing where to go and knowing what to do and training on that is the best way to do it. We can engineer as much as we can, but just knowing, hey, I got to get to a higher area is the best thing that you can do, and it'll save the most lives. We can always rebuild, but you can't bring anyone back to life. So yeah, the most important thing is having an evacuation plan. So keep that in mind. Before we go, so this is going to be our next in-class assignment. I have this assigned as due on Saturday at midnight. This is about the 7.5 earthquake that hit Palu, Indonesia. This link will take you to the USGS site that'll tell you more about the earthquake. This is what the site looks like. And this is what you're going to be working on, what you're going to be answering, and why this not. At the end of this, you're going to establish why this tsunami was unusual. So I'm going to upload this to Canvas, so you'll have it. Keep an eye on that. You're free to work in groups. You're free to work individually. You're going to be making your submissions individually. So, but I welcome you guys working in groups. And if you guys have any questions, let me know. I'll be here for a little bit, but I won't be having office hours today. So have a great Wednesday.
Thank you.
Yep.